Sometimes I like to ask myself complex questions in an attempt to see if I can come up with a simple answer, maybe an answer that most people could potentially understand. Somebody asks you, what is a black hole? What is your answer? And I would say, well, it's a structure that is so compressed and so dense that it sucks in everything, not just other structures, but light itself also gets pulled into it. It's an object with probably the most gravitational attraction that any object could possess. And it's so weird because the concept of a black hole, in order to really understand what it is, it ties into all these other concepts. Other branches of science kind of have to be evoked in order to even discuss really what a black hole is. And it's, I think, part of what fascinates me about them as a phenomenon so much, because in order to kind of think about the idea that light, which moves at a faster velocity than anything else we know of, would not be able to escape a gravitational well that's powerful enough. It's kind of like, well, then what's gravity really? Gravity is more or less the curvature of space-time via the presence of matter and energy. You could think of space-time as kind of like this three-dimensional grid that also has a dimension of time. And, you put matter and energy in that grid, and all the little points, all the little coordinates on that grid will start to twist and compress and curve and all that stuff. So it's probably not a surprise that if you got on a jet and just kept moving forward, you would think you're going in a straight line, but you're moving in a curved path, and it's supposed to be straight, but it gets curved because there's all this mass curving space, and then the mass itself becomes curved. That's why a flat Earth or hollow Earth theory doesn't really work out too well, because matter just doesn't really do that when it interacts with the space-time grid. It kind of just causes things to curve into this, this ball shape, and then objects that are not particularly large, like asteroids, tend to have more of a potato shape because you need a bit more mass than that to get that nice ball shape. So once you get to something like the sun, or any star for that matter, you're talking about a much larger object, but also a much more massive object. And the reason that there are these constantly exploding balls of gas and plasma is because the matter is just really massive. There's a whole lot of matter, and it's really close together. Smash enough matter close together, the actual nuclei of that matter will just fuse, will literally fuse. At the center of a star, it's pretty hot, you're going to get that kind of interaction. So you got all this nuclear fusion happening at the center of stars, and there's this energetic byproduct that's created as a result. So basically, if you've got two hydrogen atoms, which are the lightest atoms that exist because there's just a single proton in the nucleus, so it is the lightest, they smash together and fuse, you create, you got the fused hydrogen atom, but you also have a helium atom that is kind of spontaneously created as a result. It's part of the conservation of energy. Thermodynamics kind of stipulates that you can't really add to or take away energy from a system, you can only transform it. So the energy of the fusion of a couple hydrogen atoms will, produce this heavier atom, an atom of helium, which, has a heavier nucleus. And this process kind of continues down the periodic table, and it goes down the list all the way to iron. So it's pretty weird. You get these stars that mostly have a bunch of iron in them. It means that the star is really, really, really heavy. And despite that heaviness, which creates all this space-time curvature that tries to squeeze the star into its center, all that radiating pressure from all the thermal activity going on will balloon that star out, and it'll get bigger for a while, and it'll start shrinking because, it can no longer fuse, so that radiating pressure from the heat is not going to be as strong anymore. All that curvature from space-time being caused by the thing being there, by the star being there, will start to push everything back toward the center, and eventually it pops because you can only cram so much matter into such a small space before you have an energetic reaction like that, where you just have an enormous release of energy. That's called a supernova. Most people know about that. You've heard of that. It can outshine a galaxy briefly when that's happening. And what's left might possibly be a neutron star, where the outer layers have kind of blown out and you just have that core left. And the core is pretty small. Like a star could potentially be millions of miles across, like in terms of its radius or its diameter, I guess. And once the supernova explosion happens, you're left with a star that might only be a few miles across. So like something like the size of New York City in terms of surface area. And they're called neutron stars because most of the atomic material has blown out and you're left primarily with a sea of neutrons. And we call it a sea because it's something called a superfluid, which I don't really quite understand what a superfluid is. So according to Wikipedia, superfluidity is the characteristic property of a fluid with zero viscosity and therefore flows without any loss of kinetic energy. When stirred, a superfluid forms vortices that continue to rotate indefinitely. Now, if the starting mass of that star was significantly greater, what happens is it can bypass that neutron star kind of phase and just collapse into a black hole. Following the explosion, following that supernova, rather than getting a stable but very, very condensed, rapidly rotating, neutron star, you get kind of something that has a similar radius, it's similar in size, but its center has just been crushed to a radius that's like less than the width of an atom. Like in general relativity, that is like a zero radius sort of thing. It's like a funnel that just closes in to a point where there's just no radius. And in quantum mechanics, apparently that radius is just very, 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 very small. It's kind of not clear what goes on in a space that small. The Big Bang Theory, which is now usually called inflationary theory, or the two are sort of used in tandem to kind of refer to the same overall kind of phenomenon of a universe being born, that involves a very, very small, almost not quite zero radius, but very, very small radius kind of container of energy that expands outward, where time and space are sort of created simultaneously as it expands. And that's kind of similar to how a black hole is this very, very small, condensed space that fundamentally changes space and time when you enter it. And it's almost like the opposite with the Big Bang, where time and space are sort of created from an expanding outward. So there might be some kind of, it's almost like a Big Bang is what happens when there's even more energy that's crammed into an even smaller space than a black hole. So you kind of go from like a single atom to something that, is pretty darn small, like a single-celled organism, to something like a human, which is significantly larger, to then something like a planet, and then to a star, and then to a black hole, and I guess a Big Bang, or whatever that is. So it's like the more massive and condensed things become, you see these changes in what is actually produced, what the structure is. If someone were to ask, would you ever want to travel through one, I'd probably have to say, sure, if it's the very last thing I ever do, because you'll be crushed by getting, shoved into that funnel. I mean, if you fall down a well, you'll start slamming against the sides of the walls of the well as you fall down it. So you're going to get injured. Now, if it's a really, really wide well, you might not slam into the sides, but you're still going to get hit when you hit the bottom. It's still going to hurt. But a very, very, very large black hole would have a large enough radius that as you're falling in, you're not necessarily going to get hit by those gravitational tides, but you're still eventually going to, it's going to funnel down to a point. So even with a really, really large one, probably going to be killed. If you're going in feet first, your feet are going to be closer to the center than your head. You're just going to be pulled apart because the gravity is going to be way stronger, at your feet than at your head. So it would be interesting to do if that's like how I'm going to go out, sure. And what would be even more interesting is if I could linger at the edge of the event horizon for a while and watch the universe rapidly unfold, because there's time dilation. Time starts to really slow down the closer you get to anything that's gravitationally attractive. So, and you might see much of the universe unfold as you linger toward the edge, and then as you drop in, everything would just, you'd see the entire history of the universe. Well, maybe not entire, but you'd see quite a bit of the future rapidly unfold. And if anyone was watching you fall in, you would just sort of get stuck at the event horizon, because that's what it is. It's like the horizon at which events occur, so events don't really seem to happen once you get thrown in, because there's so much time dilation that time just basically appears to stop.